given by Professor Guy. So please stay, hang around. So from 4 to 5 today, and then tomorrow and the day after. So again, it's a great pleasure to introduce a longtime collaborator, Ionescu from Princeton. So Alex is a major expert of many things, started in harmonic analysis, then did linear dispersive PDEs, fluids, GR. This lecture, I'm going to concentrate on one of the main areas of expertise, which is water waves. And the first lecture is on the regularity of water waves. Thank you, Alex.
Thank you. Thank you, Fabio. Thank you for the very nice introduction, and it's a pleasure to be here. And I've been here several times. I've been here before, and every time it's been great. The last time I was supposed to come was during the pandemic. There was this program that I think happened on Zoom, so I gave a couple of lectures on Zoom, but of course back then in 2020 nobody could come. So it's a pleasure to be back here to talk about. I'm going to talk about some work. So this is the title for this lecture. The titles, I'm going to talk about some work on waterways, which is a program that Fabio and we started many years ago, around about 12 years ago. And I'm going to talk about work that we've done. There's a certain goal that the certain goal has to do with the wave turbulence theory. But I'm going to talk, I'm going to introduce the problems. I'm going to present a bigger picture of waterways, that it's not just about wave turbulence. So this is joint work that we've done over the last few years, all of it with Fabio Pusateri, and part of it with my former student and our former colleague, Yu Deng, who was also in Princeton at the time when we started. So I'm going to talk about the regularity of waterways. Now, of course, we've seen waterways already in the lecture, in the two lectures this morning. So I feel like, okay, so I'm going to talk a little bit about the regularity, but one should keep that in mind. Now, just before, I'm not going to, we are looking for the more advanced theorems. We are looking at, one should keep in mind there's some difference. For the more advanced theorem, we are looking at waves that are small in a certain sense. So whatever exactly the sense in which they are small, that's going to be very important. Like how, like they could be small in terms of amplitude, they could be small in terms of energy. It makes a big difference. So that's different from, they are not, like the Stokes wave, of course, is not like that. And the theory, so the real interest, because you're talking about waves that are small, it's not about the linear theory, it's about the nonlinear theory. There's nothing really you can prove at the level of the linear theory because they're small, so they are perturbations, something to understand very well. And they're also looking for stability as opposed to instability. So the subject is the same, but there are other perspectives we are going to be interested in. Okay, so yes, I'm trying to figure out how to move the slide. Maybe this one. Screen sharing. So okay, some screen sharing. That's just screen sharing. Yeah, thank you.
So that is not attached to your laptop. So
oh, that's not. Oh, I see.
It is. It should be your own laptop. So
yes, but I don't know how to make it. Okay, so let's start this again. Exit full screen. View.
Could be slideshow.
Slideshow. How did you do that?
I just clicked it. Yeah. Okay. No, I'm not sure on what this app is. So
let's try. I usually go with full screen. Oh, I think now it works. Okay, fine. Fine, I think I got it. Thank you. Sorry about that. Okay, so you're looking at the system. You're looking at water waves. So I'm going to draw some pictures. So the first couple of slides are introductory, but just mostly to set up the themes and the equation. So you're looking at water waves, so you can think of a fluid that lies under a free boundary, and there's a motion, there's a joint motion of the fluid itself, which is described in terms of the velocity. So here's the velocity u, and the velocity, of course, is only in the fluid, and then there is the interface. So the fluid moves inside the domain, so it's an incompressible fluid, so it moves the incompressible divergence of u is equal to 0, and then this is the Euler equations: dtu plus u nabla u is equal to minus gradient of the pressure, and there is the term that's specific for water, which is the gravity term pointing down. So it's a gravity term that points in the direction of points down. So the gravity term points this way. And so these are the equations of the fluid. Now we also have the equation of the boundary. So the motion is a joint motion of the fluid and the boundary. So the boundary can be described in several ways, and there's a level of imprecision in this slide because like the function z, so there are various ways to describe the boundary. There are things that have to do with the gauge. One has to fix a certain gauge in order to describe the boundary exactly. So morally, one should think is that the motion of a particle on the boundary is determined by the velocity u at that point. So dt z minus u is tangent to the surface. One could set it equal or can set it tangent. So this means that the particles, that the motion of the boundary respects the velocity of the fluid. And now there's the pressure. So the pressure is to be given, and the pressure is given on the interface. We are going to discuss roughly the Wall-Posner's theory. So the pressure is equal to a fixed multiple, sigma, which is a surface tension, times a curvature kappa over xt. So this is the mean curvature of the interface. So this is the most standard form of the standard form of the water wave problem. There are variants one can do. So there are several variants one can look at. One can do, for example, infinite bottom. So the domains could be, one could have the domain could extend all the way to minus infinity, or one could have an infinite or finite bottom. One could have periodic conditions, meaning periodic in the horizontal coordinates. So that's what we are going to have, in fact, periodic in the horizontal coordinates. One can have vorticity, one can either have vorticity or not have vorticity. One can also take modular models in which, so this is an interaction of a fluid and a vacuum, but one can take a modular model in which one have interaction of two fluids. So one would have, let's say, a heavier fluid on the bottom and a lighter fluid at the top. And now, how do we solve the equation? So I'm going to write an exact local Posner's theorem just to have an understanding that we know how to solve it. But to try to understand how things go. So if we are to try to solve the equation, at least to understand. So let's say we have the situation is given at a time t, and we want to understand the increment in order to be able to move to the next time t and to keep going. So how do we do this? Well, we can start from the fluid equation. dtu plus u grad u is minus minus gradient of the pressure minus the gravity term, and we can take the divergence of that. And if the divergence was to stay 0, then you would get, this simplifies here, and then we get the equation for the pressure, which is minus delta of the pressure is the divergence of u nabla u. And now the equations, it explains how the equations work. So what we know is we have the pressure, we prescribe the pressure on the interface, and we have an equation for the Laplace of the pressure in the interior. This means that we can find the pressure everywhere. So because we have this, it explains why is that we need to prescribe the pressure on the interface in order to be able to make this step. So we have the pressure, we have the Laplace equation for the pressure, we have the pressure on the interface, we can calculate the pressure in the interior. Now, once we have the pressure in the interior, we can go back, and if we have the pressure, then we can calculate dtu. because we know all the other terms. So we understand what dtu is. Once we have dtu, so we know how u moves, we can use the other equation to find how the interface moves. So then that, at least intuitively, lets us move to the next increment of time, and then we can keep going. So the local theory of the equation, one has to make sense of this procedure in a correct way. So using estimates and using understanding exactly how this works. And the local theory has been well developed, and is the part that's best understood. It goes back to work of Nalimov, Yoshihara, Craig, and many of the things I'm going to say have a lot to do with the University of Toronto. So, including this slide. So now it's not so simple. So the theory itself is not like the local world positiveness or the Euler equations. It's not as classical as that. In fact, the theory only became pretty well understood after the 90s and more like around 2000 after the work of T.J. Wu. One has to make sense of this story that I was telling you, that you calculate the pressure, you calculate the dtu, and then you can move to the next increment of time. But one has to make sense without losing the derivative. So it's not, there are things that need to be done. And the general picture, but the general picture is understood by now. And I put some names there. The general picture is the following, that if we have, one can have the local regularities, one can have, there's a certain condition that has to, there's the so-called Rayleigh-Taylor condition, or that's verified if the surface station is positive. Now, the time of existence, one has to be a little careful. The time of existence of the local time of existence depends on two things. It depends on the smoothness of the initial situation, like it's supposed to do, but it also depends on the so-called R-chord constant of the interface, because if you can imagine, if the interface was to look something like this in the beginning, then there's another obstruction, namely that could have been very close to self-intersecting. So then the time has to be able to see that. It's not about smoothness, this could have been very smooth, but if they were very, very close to touching, then the time would have to be adjusted to be small enough so the interface does not self-intersect. So this is the R-chord interface, the R-chord constant measures the fraction between the length of this line and the length of the chord, and the length of the arc. Okay, so this is the, so this would be, so I'm gonna, maybe the first half of my first lecture, I'm going to discuss a few problems, and then we are going to focus on the one that is the one that's relevant for the lectures, namely the long-term regularity of the problem. But for now, we're going to have a few topics that are very, very much studied in the context of waterways. Now, once we have the local regularity theory, there are at least two basic questions one can ask about any equation. Is there, once we have solutions that exist locally in time, do they exist globally in time, or do they form singularities? So understanding the formation of singularities is a huge problem for fluids. This it's very far from being understood. Understanding formation of singularities for incompressible fluids. You see the equations themselves, the waterways equation, they contain the Euler equations. So one cannot hope to understand formation of singularities in the interior of the fluid without solving the problem for Euler. If anything, you know less, because you have to control the movement of the interface as well. So if anything, it's harder so one cannot imagine to understand that without understanding well the formation of singularities for fluids, for the usual Euler equations. But there's a certain form of singularity that can form because of the interface. And the simplest, the only one that's been proved that's known by now is essentially to make sense of this picture. Namely, if there is a fluid that one can arrange a singularity of the following type, that with a fluid in a situation like that in which the interface is almost self-intersecting, and one can arrange in such a way that the initial velocities, they point in the opposite ways at the point where it's almost where the interface is almost self-intersecting, and one can arrange a local world positiveness theory on a time that's long enough in order to lead to the self-intersection. So this is the so-called splash singularity, and it was discovered about 15 years ago by Castro, Cordoba, Pfefferman, Gancedo, and Gomez-Serrano, and there's an independent paper, a separate paper by Coutin and Scholler. So that's this is the only singularity that's known for this model. It turns out it's not a very robust singularity because we found this a few years later that while it can happen in the context of the water wave interacting with vacuum, it cannot happen in the context of water wave interacting with any other fluid on top. So the singularity, even if the other fluid has very small density, it just cannot happen. The so-called splash singularity cannot occur, not in a way that preserves the smoothness of the interface. Now, what would be more robust singularity, but that's not known, is to show that this self-intersection can happen while at the same time forming a corner, which would mean a formation of corner at the level of the interface, and that's in principle, one could hope that something like this is possible. There's no obstruction to it's possible, but it hasn't been proved that it does happen, that there are any scenarios that lead to that. So what I mean to say is basically the formation of singularity is a wide open problem, and the only result that's known is this displaced singularity of these authors.
Of course, also with surface tensions or without surface tensions.
It makes no difference. It makes no difference. You can even put Navier-Stokes. It's robust enough that it's basically this picture that in this such a short time you can arrange that this time is you can basically draw the surface that you want, and in such a short time that even if you were to have Navier-Stokes, it will not make a difference. All of this interface, the interface stays smooth here, so the surface tension also doesn't make a difference.
And I would expect that maybe surface tension avoids for later time the corners or other.
This has nothing to do with corners. So the interface will stay smooth, and just because it started very nearby and can control the time of existence a little, like for a short period of time, that's enough just to lead to the self-intersection. So this, in principle, the surface tension could affect if there was to be a corner, but there's no corner here. Okay, so that's the problem, the formation of singularities. Now, the problem I'm going to talk about that's more related to the rest of the lecture is the long-term and global regularity. So long-term and global means that, of course, you have the solution on a short period of time, and we want to understand under which circumstances we can control the solution for a long time. So we can construct the solution for a long time. One should keep in mind all of this. It's much more specialized. So the situation I have here is a general situation. It's the fluid doesn't have to be rotational. In some sense, the domains, they matter much less. The long-term and the global regularity theory is something much more specialized. It only happens, we only raise these questions if you're talking about small, so the solutions are small, and that exactly in which way they are small, that's going to be important, but not to think of them as small. And one can have gravity, one can have surface tension. In the problems I'm going to talk about, we don't have finite bottom, and we are either in 2D or 3D. And most importantly, the waves are irrotational. So in order to the other questions, it doesn't matter that the waves are, you could have vorticity, but for the question of global regularity, we are talking about irrotational waves. And there are several results. I listed a few results here. Going back, they are not that old. They go back to the first long-term results like that were obtained by CGO. I've listed a few results depending on exactly which model one looks at. There's also so these are, some of them are in the Euclidean space. In the periodic case, there's work of Massimiliano and his collaborators. It's a different mechanism. So we are thinking here, the mechanism we are talking about here is something that is basically dispersion, a mechanism that one would look at in the periodic case has to do with the periodicity or quasi-periodicity. So there are different mechanisms, but one can raise these questions in this setting as well. It's a more specialized problem in the sense they're only talking about irrotational water waves and also small in irrotation. Now there's a very beautiful topic that this is in some sense the most classical one, and we've already seen a lecture this morning, which is about steady solutions. So steady solutions for waterways, You can do steady solutions for other equations as well, but for water is a particularly prominent topic. And of course, this is the Stokes wave, the one that Massimiliano was talking about this morning. So understanding and there are really very nice open problems there, like very natural open problems. Like, for example, this, I find the beautiful open problem, the existence of overhanging profiles. These are not the Stokes waves. The Stokes waves, they are not overhanging, but whether one can have these steady solutions, and one can have steady solutions, or one can have them in the periodic setting or in the Euclidean setting. So there are lots of beautiful problems here. And in some sense, this is the most classical. These are the most classical of the waterways. In order to construct, one can talk about the local bifurcation and then the global bifurcation in order to construct really large solutions. So that's another topic that's been very much studied. And two other research directions that I'm not going to talk more about, but they're also connected to waterways. Waterways are very rich, and one can take many asymptotic regimes. One can take many types of limits. And at least there are lots of other equations that basically can be constructed in some sense special, like special cases of the waterways. And for example, the KdV, the Korteweg-de Vries equation, the Benjamin-Ono equation, the Schrödinger equation, it's all water-wave equations under certain regimes. Like you can have like it's usually 1D models. But under certain regimes, like in shallow water, for example, the Benjamin-Ono, so there are various regimes that in the limit lead to these equations, but then afterwards one can study these equations separate. So for example, the KdV and the Benjamin-Ono, there's been a lot of work done because they're also completely integrable equations. So one can do a lot of work starting from there. The Schrödinger equation, of course, that's something that's been studied a lot as well. And so that's a completely different, it becomes a completely different topic. And of course, there's another important topic, the topic of numerical analysis, mainly because these waterways, they are very complicated. And sometimes one can only understand them using numerics. Now, at the level of, so this is like, this is a broad general introduction of the topic of waterways. We are going to be focused only on one topic. So there's very few of these very few of these solutions are stable. So if we think of the steady solutions, very few of them are stable. The only one that we know to be stable is the zero solution. The only one that we know for sure that is stable under very robust situations. So this is if you want to, we are in that kind of setting in which we are perturbing around the zero solution, and exactly how we are perturbing, that's the topic of the lecture. And so the goal is to understand this long-term regularity and with the motivation. So long-term regularity, one can do long-term regularity in various ways. The motivation in our case is going to be to understand the wave turbulence, how wave turbulence develops for waterways. So it's going to be one other aspect that I didn't mention here because it's not one doesn't have to bring it in the beginning, namely that the initial data, there will be a probabilistic aspect. The initial data, in order to be able to observe wave turbulence, the initial data has to so one has to bring in probability. So we are going to be talking about samples of data. Okay, so let's. Okay, now for irrotational waterways, we already seen the equations in the morning. The picture is different for irrotational waterways. One can write the equations in a more efficient way, and it's a very simple reduction, and I'm going to explain it briefly on the slides. It's a simple reduction that goes to the fact that if if the fluid is irrotational, then one can write it as a gradient of a potential, the velocity field. So you can write the velocity field as the gradient of the potential, and the potential is it's a harmonic function from the divergence equation, and then so the efficient variable in order to write So basically, if we count the variables, we usually have lots of variables. So we have the fluid inside, we have the interface, and we have some conditions, and we want to understand this equation more efficiently with a smaller number of variables. And it turns out that the best way to do that is to think of the potential, because the potential already is a harmonic function, is determined by the restriction of the potential to the boundary. So these are the two variables one needs to look at: the restriction of the potential, the function little phi, and the function h, which describes the boundary. So I'm going to think we are going to think there's one more restriction here, namely that the solutions, the domains, they are below the graph of a function. So the domains are described by a function h. So we are fixing the Eulerian coordinates for the in the problem. Okay. So in any case, my point is that in the case of irrotational waterways, one can describe the whole problem just in terms of two functions, little h and little phi. Not only there are only two functions, two scalar functions, but they also are defined. They depend on one less variable than the full domain. So they are defined only on the interface. And this is the system. That's it's a very important. It's the simplest way to write the waterway system. So dth is gh phi. So I'm going to describe in a minute what is this object gh phi. Gh phi is the Dirichlet-Neumann map associated to the domain A, to the domain defined by the function h. So the equation is dth is gh phi, and dt phi is minus gh plus. So this is the gravity term. This is the surface tension term, which is sigma times essentially the second derivative of h, because if you remember, that had to do with the curvature of the interface. And here we have two velocity terms, two quadratic velocity terms, grad phi squared and gh phi squared. So this is the system in this economic form, is the so-called Zakharov-Craig-Shank-Sulem system formulation of the waterways. It's the right way to look at it when we are talking about irrotational waterways. Now, how does one derive it? So it turns out that the derivation is simple. If we just think of the velocity equation, so we think that basically, so I wrote one of the equations. So we wrote that the v component is the gradient of phi. So the equation of the form dt dk phi. And then we have dj phi, dj dk phi, and then gradient of the pressure, and then g times, and we think of the vector pointing down as the gradient of y. So that's so this is the equation. And now we can notice here, so the dk derivative simplifies. So this would be for all the k's. And when it simplifies, we get something like dt phi plus grad phi squared is equal to the pressure plus g times y, only after we simplify the dk derivative. And now we know the pressure, so now we restrict to the interface. We know the pressure on the interface. So this term, so the pressure on the interface has to do with the sigma times the pressure on the interface is like sigma times two derivatives of h. So that's what this term is. This term is g times y, and y on the interface is h, and this is some quadratic term that has to do with gradient of phi squared, which are the gradient square, and we can retrieve all the terms here. So this is dt phi, this is minus gh, which was coming from the y term. This is the surface tension term, and these are the quadratic derivatives. One has to work them out exactly, but this is how they come in. And the presence of gh phi, so the presence of gh phi has to do with the fact that gh phi is basically it's a velocity. So it's the velocity. So the first equation, I present the first equation, has to do with how the interface moves with the fluids. So we know that we know that the dth is supposed to be equal to the velocity, the normal component of the velocity to the interface, and that's described by gh phi. So gh phi is that component. So that's how the system makes sense, and eventually one gets this exact formulation. That's the formulation of Zakharov, Craig, Schenk, and Sulem for the system. And it turns out that this system also has a conserved energy. It's not so easy to prove in this formulation, but if you think where it's coming from, it's actually pretty easy to see. It's coming from the original energy of the fluid. So this is Hamiltonian, and it can be written in this form, and it has several components. This is the components to do with the potential, and here there are two components that have to do, two energy components that have to do with the interface. Okay, so this is the system, and now if we look at it for a minute, it looks like a pretty. If we want to prove now, let's say you want to prove the local regularity theory, at least in this setting, so in the case of rotational waves, it looks like it's the kind of thing we can understand, and we can try to prove energy estimates, for example, to prove the local regularity. Provided there's only one thing that's mysterious here, namely this Dirichlet-Neumann operator. So the Dirichlet-Neumann operator, it's actually not mysterious. We are giving the function phi in a domain, and we want to extend the function phi, find the harmonic extension, and that's the normal derivative there. It's not a mysterious object, but we need to. One should keep in mind it's not so easy because the regularity. One cannot pretend that, for example, the interface is regular, and then solve the system for phi. The regularity of the interface affects the regularity of the potential and vice versa. So they are coupled. So one has to make sense of the whole theory together. So that's the difficulty. That's why it's not a classical theorem. It goes back to the late 90s and much more work done in the year around 2000. But understanding the system is not so simple because one needs to understand the Dirichlet-Neumann operator in an efficient way, in which you keep in mind that the interface itself is not going to be much more regular than the potential. Okay, so I'm going to describe a theorem that I'm going to state quickly a theorem such that to have an exact theorem. We are going to also introduce certain objects, which are going to use them later on in order to state more theorems, in order to be able to work with this system. So the focus is going to be, from now on, the focus is going to be on this system. We are going to for us, this is going to be the waterway system. And in fact, very soon we are going to set sigma is equal to 0, which means that about half of the second equation is going to disappear. So that's so this is the system. Now, how do we prove a few things? So what we want to understand is what I like to understand is to have like what's involved in analyzing the system, I like to understand basically a form of the local regularity theory. So to understand, have a theorem that explain how to prove a local regularity theorem, and then explain how to prove long-term regularity. Oops, I'm the wrong way. And there's this object that you've seen in the morning as well, the so-called good unknown. It turns out that one cannot really work. There's an issue of loss of regularity. One cannot work with the potential itself. The most natural variables would be H and phi, but those don't cooperate well at the level of regularity. It turns out that they influence each other's regularity, but in order to get the right kind of variable, one has to do this combination. The combination is a combination of phi. So instead of phi, we are not working with phi, we work with phi minus this paradifferential operator TB applied to H. One should think of TB. So B is one of the velocity fields. So B and V, these are at the level of gradient of phi, and so these are basically velocity fields. And then we're applying here TB applied to H. So there are two velocity fields, and we're applying the velocity field B to the function H, and here So these are the objects that we are looking at. In order to understand the regularity, one has to think of this so-called good unknown. And now, as I was saying, the equation itself would all be pretty simple to understand, except for the term GH phi. So what in order to be able to make progress, you need to say how much is GH phi in terms of the other variables. And here is the theorem. The proposition is the so-called parallelization of the Dirichlet-Neumann operator. So GH is this operator you want to understand. This is not about what the well posedness of the water. It's the general theorem about how you understand this this Dirichlet-Neumann operator without losing regularity. So without being at the optimal level in terms of regularity. So the claim is the following: the GH phi is this operator, the differential operator. The differential operator, I actually have it defined on the next slide. So the differential operator depends on a symbol and the function, and it essentially, it's as if one takes the Fourier transform of the function and applies the symbol, and one should think that the function is high frequency and the symbol is at low frequencies. There's a certain way, like for example, when applying derivatives, one can apply derivatives, one can apply multiplication of operators. So there's this paradifferential formalism that allows us to take derivatives of functions, but at the same time, derivatives that are not exact derivatives. One can take this kind of more generalized derivatives defined by the symbols A. So the symbols A, these are symbols that depend on both there are symbols that depend morally both on frequency and space, and one has a description in terms of, so A tilde is the Fourier transform relative to the space variable. Okay, so T is an explicit operator. So the Dirichlet-Neumann operator is the explicit the differential operator is an explicit operator. It depends on a symbol and a function, and morally one takes derivatives of one takes the symbol is at low frequency and one takes derivatives of the function. And then the claim. So the claim, the Dirichlet-Neumann operator GH phi is basically this paradifferential operator applied to omega, so to the good variable, plus a divergence, an exact divergence, plus an error that doesn't lose derivatives anymore, which is smoothing. So we have an almost exact formula for the Dirichlet-Neumann operator, except for the term G2, which we only get bounds. But other than that, we almost know what is the Dirichlet-Neumann operator in terms of paradifferential operators and the functions H and omega. It's not in terms of phi anymore, it's in terms of omega, the good variable. And if we read it, what it says, so here we have this is lambda, this is the main multiplier. So this is the divergence. This is the divergence of H, of TVH. Now the more important operator is this symbol of the Dirichlet-Neumann operator, and it has two parts. And if we want to read it, it has a linear part and a nonlinear part. So here we have the second part is less important, so let's just focus on the first part, which is at the level of one derivative. The first part, lambda 1, is at the level of one derivative. So what it says is that we have the linear level, it's simply absolute value of xi, square root of absolute value of xi squared. So morally, this Dirichlet-Neumann operator is a perturbation of the absolute value of xi, because it's square root of absolute value of xi squared. So it's absolute value of xi. So at the linear level, at the top order, so let me write this down. GH phi at the top order is this operator, square root of the Laplacian applied to omega plus lower order terms. The lower order terms, they're not really, one needs to understand this exact expression because they're the same level of derivatives as the top order. So one has to be careful with that, but this would be the simplest way to think of the Dirichlet-Neumann operator. But more importantly, here we have an exact formula. So up to smoothing errors, we have an exact formula for the Dirichlet-Neumann operator. And once we have So once we have an exact formula, we can go back to our equation, which is this equation over here. We understand this would be basically absolute value of phi plus other terms that work out when you do energy estimates, they work out in a similar way. There's the right these operators here, they have the right symmetrization. And using this, one can prove energy estimates, and one can prove the local regularity theory, namely that if H and phi they are both smooth, then one has local existence of the solution on a short time interval. So that's what's involved. It's not a complicated proof. What took some time is to understand that basically one needs to understand this Dirichlet to Neumann operator in a very precise way, because we need to understand it at the level of what are the derivatives. Here there are various combinations here that they all matter, so it matters to put them in this way in order to be able to close the energy estimates. Okay, so this is the local. So this is the first theorem, the local regularity. Now, what we want to do, we have local regularity. There's no issue as long as we work in these Eulerian coordinates. I mentioned earlier that there's also the issue of the self-intersection of the interface. There's not an issue anymore as long as we work in, as long as our interface is a graph and we work in Eulerian coordinates. That there's not an issue. It's just a regularity issue. Okay, so now we have the local regularity. And now we are ready to move towards the long-term regularity. So my goal is to understand the long-term regularity of this equation. This is the same equation as earlier, except that I set sigma is equal to 0. So I removed, as I said, about half of the equation. I removed the term that had to do with the sigma here. It was the second order term in H. So this is the most pure gravity waterways. They're thinking of the gravity, the waterways as being one-dimensional. One doesn't have to, for what we've done earlier, one can have multi-dimensional waves as well. It makes no difference. And actually, the theorem that I had, the local regularity result was written for multi-dimensional waves. But in order for the long-term regularity, the dimension matters. They're going to assume that we are in one dimension at the level of the interface, which means that the waves are two-dimensional waves. But at the level of the interface, they are in one dimension. It's in some sense the simplest picture is the kind of picture like the Stokes waves, for example, that we've seen earlier. These are the most natural waves because the propagation of waves, waves are really a one-dimensional object. And we are going to think of H and phi. So this is the system that we are working on. We are thinking of H and phi as being small, meaning small perturbations of 0. And how exactly we measure smallness, that's important. It makes a big difference how we measure smallness. We can measure it at the level of the L2 norm. So that's a pretty strong way to measure. Or we can measure it locally, the smallness, so one can measure just the amplitude of the waves being small, but a very big energy. Or one can measure the waves as being small and localized. So not only they are small, but there's nothing happening outside. There are basically at least 3 ways to measure smallness, and it's going to make a big difference at the level at what we can prove. Okay, so that's this is the problem we are going to talk about for the rest of the lectures. Now, here I wrote, just to keep things simple, so I wrote that the functions H and phi, they are defined on the Euclidean space. And one should think of them as being defined on the Euclidean space. That's the easiest way to think. Formally, it is going to turn out that H and phi, we are going to have to take some limits. H and phi, they're not, we want to think they're not just defined on the Euclidean space, but they're also defined on a big torus of radius r. So one can take a big torus of radius r times the time interval. And the theory works almost the same way. The torus, the radius r of the torus is always going to be bigger or equal than 1. And the theory, so one can think of the real line as corresponding to r going to infinity, and everything works out. There's no, the limit is it makes sense in that setting. Okay, so this is the problem that, this is the long-term regularity problem. Okay, now how do we look at the long-term regularity? The first thing I'm going to describe is the so-called, one very important aspect to keep in mind is the issue of resonances. When you talk about the long-term regularity, it's not about regularity itself, it's about the fact how the waves interact and what are the resonances. And what I want to describe first is a theorem that is not our theorem. It's a well understood theorem, namely the fact that for this system, for this the pure gravity system in one dimension, there are no resonances, which means that we want to understand. I want to understand basically what's called the quartic energy inequality. Namely to show that the solutions in a general kind of situation, the solutions extend on longer times. And how do we look at a system like that? It's not about it's not about regularity anymore. It's about resonances. So we want to understand how do the resonances, what are the resonances, and how do they what do they say about the waves? And the simplest way to do it is to simply linearize the system. So if we look at linearize the system, as I wrote it here, GH phi is now nabla of omega. One could also think of nabla of phi, because at the linear level is the same. So the equation would be dth is equal to nabla of phi, and then dt phi is minus h, because these are the terms that they're all nonlinear. So the linearization of the system around the zero solution is dt h linear is equal to nabla of phi linear, and dt of phi linear is equal to minus h. And okay, this one can solve. And there is a certain way to solve it efficiently, namely to use one complex variable in order to get, it's a little easier to work with the complex variables in this case. So complex variables, we call u lim to be h plus I times absolute value of nabla to the 1/2 times phi lim. Turns out that one has to diagonalize this system. So what we like to say is to write an equation of the form dt of some variable plus some operator applied to the same variable is equal to 0 in order to be able to solve explicitly. So the combination that I put over there is in such a way that the system that I wrote at the top, in terms of h and phi, it becomes diagonal. And it becomes diagonal in this form. And so at the linear level, we simply have dt plus I lambda u, which is this part, is equal to 0. That's at the linear level. At the nonlinear level, we have to put a nonlinearity. Assume we know how to do the local theory, so I'm not going to think anymore about the possible loss of derivatives, at least for the purpose of this explanation. So I'm going to pretend that the nonlinearity is more explicit, because basically I want to get the point, like what does it mean, how do we understand the resonances, what does it mean the quartic energy inequality. So I'm going to pretend that the nonlinearity is a more favorable form than the one that it really has. And the more favorable form is basically a product. It's a product of the velocity v and dxu. A product up to a certain multiplier that's localized in such a way that the frequencies c and theta are proportional. And v, so the velocity v, is obtained as dx. So there's a certain symmetry as to do with the real part here. So we basically have a nonlinearity that's of the form dxu times u with certain multipliers that respect the Hamiltonian structure of the system in order to be able to prove energy estimates. So in order to explain how, like, the simplest kind of long-term regularity result, I'm going to pretend that this is the system. And one can reduce the real system. Once you understand how the local theory works, so you already have an understanding of the Dirichlet-Neumann operator, one can morally reduce it to this system, the proof. But this is simple enough that I can write it down. Okay, so how do we prove, what do we want to do? What we want to do is to say that if we're looking at this system, so this would be a simplified water wave system, what we like to do is to say that if we start with data of size epsilon, then the time of existence, if we were to have a general system, it would be 1 over epsilon, like the general theory, you start with data of size epsilon, the time of existence is 1 over epsilon. What I'd like to say is that because of the way the resonances work in this system, the time of existence is actually 1 over epsilon squared. So it's much bigger than 1 over epsilon, it's 1 over epsilon squared. So this is the first step. And that's what you're looking to do. So you're looking to prove long-term energy estimates on these longer time intervals. Okay, so how do we do it? We want to prove energy estimates. So we define the variables. So we want to prove it. We just use Sobolev spaces. So you want to prove energy estimates. So we define the variable, the differentiate variable. U was the original variable. We want to take derivatives of U. So we have this variable W. And then we define the energy, the most simple energy we can think of, in which we take so we take the L2 norm. This doesn't matter, it's Euclidean or on a torus. It makes no difference here. So I'm leaving it a little imprecise here. So it's written on the Euclidean space, but one can do the same calculations on the torus. And then we are looking. So the energy is being defined as by this is the nth order energy. So you take n derivatives of the function u, and that's and then we take the L2 norm, and then we calculate d by dt of the energy. So we want to understand the energy growth. We want to say that the energy starts out at size epsilon squared, so time t is equal to 0 to d epsilon squared, and on a long enough time, epsilon to the -2, it does not more than double. So it doubles up, but it still stays the same size as it started. Okay, so you can calculate d by dt of the energy. And then when we calculate d by dt of the energy, here we have the nonlinearity, and we can plug it in. So d by dt of the energy. This operator is purely imaginary, the way it's written here. So there's no, it's basically because it comes from Euler, there's no growth of energy, no exponential growth. And what we get is that d by dt of the energy is a combination of W and the velocity term at that was coming in the nonlinearity. And there's a certain multiplier. It's all written in terms of multipliers. The multiplier, once we combine it carefully, we get, so we write the multiplier. So the energy is something of this form of W of eta, W hat of W bar of xi, and then the real part of U at xi minus eta times a certain multiplier. And basically the multipliers, I wrote it here explicitly. It's a little hard to see what it is, but it has, there's some symmetrization, there's some symmetry in it that allows for the energy to go through. That's inherited from the way the form that I had for the operator. It's basically inherited from the Hamiltonian structure of the system. Okay, so now if we just write it like this, we get, and we integrate, we get that the energy at time t minus the energy at time 0 is controlled by the interval from 0 to t of the energy at time s times the L infinity norm of the solution u, which is basically, which would give the time of existence of size 1 over epsilon. Now, what we want, the so-called quartic energy inequality, which is the simplest form of long-term regularity, is to prove the same inequality, except that the integral is the integral of the energy, but you would have the square of the term with a smaller number of derivatives. And I'm willing to allow more derivatives here just to simplify the proof. And now we also have to change the energy. So the energy is going to end up with this, when we integrate by parts, you're going to end up with one more term in the energy. So the point, as I say here, the point is to get two factors of this low frequency term in the right hand side in order to be able to have better decay. If you imagine you have two factors, each one of them counts as an epsilon. So the energy does not more than double on a time of existence of size epsilon to the -2, which is the goal of, which is the first goal of this quartic energy inequality. Okay, so how do we prove something like that? And we can look at, there are various ways to prove it, and I'm going to describe the kind of way that Fabio and I, we see these things pretty, that we've developed. And now, the original proof of this was given by C.J. Wu. So the original proof of the quartic energy inequality for the gravity waterways in 2D was given by C.J. Wu. This is our proof that we've been working on in various ways. And we want to, so basically what we want to do, what we want to do is to integrate by parts. So we want to understand the normal forms. We want to integrate by parts in time. And we also want to rewrite things in terms of the so-called profiles. So the profiles means that we are looking at the solution, but the solution already has a certain, the solution at time t, it evolves at the linear level, and we want to take back the free evolution and to write everything in terms of profiles. And when we do that, basically I want to write this term. So this is the bulk term, the one that the one that's going to measure the increment. And when we do that, so W is going to pick up one oscillation. W of eta is going to pick up one oscillation. W bar of C another oscillation, and the U is going to pick up other oscillations. So at the end of the day, we end up with an integral of this type, e to the minus is. I wrote everything here. So it's integral of the type e to the minus is times oscillatory phase. And this is the profile. These are the profiles of the functions, all the derivatives, and this is the profile of the function u. And now you want to integrate by parts in S, so you have to integrate this integral from 0 to t, and you want to integrate by parts in S. And you notice what happens. So this is the key feature of the equation that allows for this long-term regularity, namely that the phases that we get here, lambda of c minus lambda of eta minus lambda of c plus minus lambda of c minus eta, they do not vanish. It's important. So this is the absence of resonances. It means that they do not vanish, and then this means that we can integrate by parts the exponential term over there. So the important thing here is that, so let me write lambda of c is absolute value of c, and the non-resonant condition that is the first long-term regularity result says that lambda of c plus minus lambda of eta plus minus lambda of c minus eta. So any combinations of this type, they are different from 0. Except in trivial cases in which one of the frequencies is equal to 0, but then the multiplier itself, the multiplier I had it written on the previous one, the multiplier itself vanishes. So we don't need to deal with that case. C to the 1/2, yes. This C to the 1/2, yes. Okay, so if you think, how is this true? So if you have a square root of A plus square root of B, square root of A plus square root of B cannot be equal to square root of A plus B, because it's the only way. So this would be square root, one of these square root of A, square root of B, and the only one that could have been bad is when square root of A plus square root of B could have been equal to square root of A plus B, because otherwise there's going to be positive, and that's not possible for the square roots here. So that's how this inequality fails. That's how this identity fails. Okay, and now, okay, so the plan is to integrate by parts, and then we need to see when we integrate by parts, the derivatives are going to hit the other terms, and then we need to establish the equation for the other terms. Okay, so I actually only wrote the result. So that's what happens here. So we integrate by parts this integral, and what do we get? When we integrate by parts, we have two boundary terms that are going to tell us how do we have to change the energy. The boundary terms become part of the energy. They are going to add up into the energy. And then the d by ds is going to hit these various terms. And then we look at all the terms. We have various terms that come up. We have cubic boundary terms, the cubic boundary terms, which are of the form what we had before, but to this additional denominator. And then we have quartic space-time integrals, which are coming from the case when we were taking the derivatives. I wrote one of them here, but there are others of the same type. They are coming when we, from the case when we take the derivatives on the function w, and they are quartic because when we take the derivative of w, we are going to get another quadratic, and we have already two more terms. So at the end of the day, we have four terms, w, w, u, and u. And then there are more complicated symbols that account for the fact that we had lots of, there were various combinations of symbols originally, but then we can bound all of these terms. So it turns out that the cubic integrals, the denominators do not bother us. The denominators, they don't have, they are not zero, so it turns out they don't bother us at all. So the cubic integrals are controlled by the corresponding quadratic energies. And at the end of the day, the quartic integrals are what remains. And what's important for the quartic integrals, we have two copies of the high frequency factors, the W's, and 2 copies of the low frequency factors. And the symbols themselves, they are in such a way that you do not lose derivatives. So that's a longer calculation to arrange all the symmetries to work out. And at the end of the day, once we put all of this together, we get the control that we want, that the energy, this is this modified energy, En prime is the modified energy in the sense that we started the usual energy and then we picked up 2 more, we picked up cubic terms coming from the boundary terms in the integration by parts. So this is what En prime stands for. And bulk terms, they are quartic terms in which you have 2 copies of the high derivatives terms and 2 copies of the low frequencies. Okay, so this is the most basic long-term regularity result for the gravity waterways, which says that we have this kind of control of the energy, the so-called quartic energy inequality. And if you see what this means, if the energy origin is of time epsilon, this L infinity norm here, it's going to be controlled by the energy itself, and each one of them contributes a time epsilon. So as long as the time is smaller than 1 over epsilon squared, this integral is smaller than a factor like twice like a multiple of the original energy. So the energy does not more than double in time epsilon to the -2. So this is the conclusion here, and that leads to the quadratic time of existence. Okay, and so this is the most basic form. One thing I didn't emphasize, but it's important later on, is that the term here that controls the increment, which is the most important term, is expressed only in terms of the L infinity norm. That is not expressed in terms of the energy. If one does it carefully, we have to estimate terms of this type. And if one does it carefully, it turns out that on the low frequency terms, we have to put only L infinity norms. Not L2 norms, it's really just the L infinity norm that we can put in. Okay, so that's so this is the summary of the simplest kind of long-term regularity result for the simplest equation, the gravity waterways, which is quadratic lifespan of the solution. Now, so what I want to do going from here, I'm going to present four theorems. So four theorems. The first theorem is to prove an analog of the so-called quintic energy inequality, in which we are not going to control only the quadratic energy, but the next order energy, which is the quintic energy, and that depends on more. It's much more specialized inequality. It depends not just on the resonances, it depends on the more complicated type of resonance, the so-called Benjamin-Fair resonances, and the absence of those. So we are going to prove a quintic energy inequality. Now, using the quintic energy inequality, we are going to prove a long time of existence result, in which we want to talk about, in which the time of existence is not epsilon to the -2, is not epsilon to the -3, is epsilon to the -6. So it turns out that there's something, one can do much longer time of existence. It's actually the same hypothesis that the energies of size epsilon, one can take a much longer time of existence of order epsilon to the -6. So there's the second theorem. The third theorem is a theorem that Fabio and I, the first theorem Fabio and I proved, namely that not only one can get a long time of existence, but one can actually get a global solutions. It's very hard to get global solutions. There are very few examples when one can get global solutions, but the gravity waterway turns out it's one of them. That one can get global in time solutions for small gravity waterways, and small in that case means more than just small energy. It means small and localized energy, in the sense that the solution is small, but it's also decaying at infinity. So this is the third result, and the final result that I'm going to discuss. It's an extension of these results, in which we are looking to understand the wave turbulence theory, and for this we have to understand long-term regularity. Morally, what we need to understand is long-term regularity, but for waves that are like in the ocean, waves that are not small at the level of the energy. Because if you think of the ocean, in some sense, the primary weakness of this theory is that one has to have small energy, but the ocean doesn't have small energy, because the ocean is very big, and one what we like to do is to understand the smallness only at the level of the local energy, so the amplitude of the waves, and to still construct long-term solutions. And that can only happen in the probabilistic under probabilistic assumptions, and leads to so eventually is going to lead to the wave turbulence of the waterways. So this is the plan. Now let's start with a theorem that's kind of analogous. My hope was to actually get through it today, but probably I'm not going to get through it. It's analogous to the theorem that we've already seen, the quartic energy inequality. So let me state it exactly, because this is work. So this is work that is joint work with Fabio and Yu Deng. So here I stated it exactly. So the statement is the following: we are looking for initial data. It's it turns out that we also want to work on a bounded domain as well. So this works on the torus so we are looking at x. The variable x is on the torus of radius r, and this is the equation, the same gravity water wave equation that I had earlier. Dt h is equal to gh phi, and dt phi is something else. And then we are thinking that we have initial data. So I think of a solution on a certain time that is for which you control the energy. It turns out that the right way to control the energy is in terms of h, and this half derivative of omega. If you remember how we defined the main variable was u is equal to h plus I times half derivative of the phi. But if we want to state an exact theorem, then we have to work with the good variable. So in any case, so we have a solution that we know a priori that lives on a certain time interval, whatever it is, and we know control uniform. We know control of this solution. Then the conclusion is that the energy of the variable, which is I plus I dx to the 1/2 omega, is controlled at time t2 by the same energy at time t1, and the increment. So the whole point is the increment. The increment is this a squared times integral from t1 to t2 of epsilon cubed. So this is the quintic term in which we have two components of the energy and three components of the L infinity norm. So it's so the increment is not quartic, it's quintic. So there's the main difference. It's a much more specialized inequality that it actually works only for the gravity waterways. It doesn't work for gravity capillary. It doesn't work in higher dimensions. Something much more specialized for gravity waterways. Okay, so that's the first theorem. I'm going to describe how it works. So the setup is the same as before, and the only difference is that we need to control the increment using a quintic term, not a quartic term, but a quintic term. And so the point, and not just that, another important point is that the epsilon, so the epsilon, the part of the increment that I call epsilon of s, depends only on the L infinity norm. Cannot depend on an LP norm, definitely cannot depend on an L2 norm, and you would start losing even if it were to depend on the LP norm. So it's important that this it's really just, if you picture what you want to address is if you have a big ocean, then the energy is going to be big, but the amplitude, the L infinity norm, could be small. So this is going to be the situation we're in. One cannot put any other LP norm, because any other LP norm, for example, would be big, would have to do with the size of the ocean. So that's the motivation for this. In order to be able to get somewhere, it has to be of this type. As I mentioned earlier, quartic energy inequalities, and I described the proof, they've been proved before, and it's a much more general thing, the quartic energy inequality in dimension 1 and 2, and they depend on the so-called absence of quadratic resonances, which is what I described earlier. This problem has some history. So the earlier work of Berti, Feola, and Pusateri, so they proved this quintic energy inequality on the torus. So in the periodic case when X is on the torus, and by a different method using Birkhoff normal forms. And CGU also proved a quintic energy inequality for the Euclidean, so she proved a similar theorem What we needed, however, was to have this right-hand side here. What's important for the application is to have the term here exactly expressed in terms of the L-infinity norm of the wave, which of course is not an issue on the torus, but in the Euclidean case, an issue, and that's so that's the main novelty here. Now, as I said, so the motivation for this, I'm going to describe the proof in a few minutes, but I wanted to explain a few to talk about the motivation. So the motivation is just to do with the so-called Hasselmann theory of climate variability. So we basically want to apply this as one part of the argument. We want to apply this to solutions, to randomize solutions of the waterway system, and the issue is the following. In order to be able to understand waterways, we need to do energy estimates. So this is going to play the role of our main energy estimate. It's not possible to expand just in terms of trees and just expand the solution in terms of the Duhamel formula, because there's a loss of you cannot do that locally. Never mind, one cannot even do that locally. So the only way to close an argument has to be close to an energy estimate, and we like to use this type of energy estimate, this long-term, this quintic energy estimate as the energy estimate for that. It comes from the need to have something like this comes from the fact that the problem is quasi-linear, so one cannot describe the solution in terms of a Duhamel formula or anything that does not involve an energy. And now the randomization. So we're going to talk about randomized solutions, and this is the randomization that allows us to control the L-infinity norm. So if we have solutions that have a controlled energy, if we were to know that they are randomized, so if one could keep the control of the randomization, then this would give an L-infinity norm, as if the solution is uniformly distributed on the big torus. So this means that the L-infinity norm would be the size of the energy times r to the -1/2. So that's going to be the plan. But for now, let's just look at how do we prove the quintic energy inequality. So this is the quintic energy inequality we want to prove, and let's just look at what's involved in the proof of the quintic energy inequality. So we start the same way as before. So we start with dt plus I dx to the 1/2 u is some kind of nonlinearity of u and u bar. As I said, in order to be able to prove the quadratic energy inequality, we need to know that there are no solutions of no quadratic resonances. And this system, the way I wrote it here, is the same as this system with the plus minuses. So there are no solutions, there are no numbers no real numbers except for the 0, in which the frequencies add up to 0, and this kind of combinations they add up to 0 as well, and that's easy to see. And that, as we saw, that leads to the quadratic energy inequality. Now, in order to move to the next level, it turns out that one needs to show that there are no resonance. What would like to say is there are no resonances, there are no so-called four-wave interactions. So there are no resonances at the next level. So you can see what the next level would be. We have four frequencies, they all have to add up to 0, and all the possible combinations here would have to be different from 0. That would be the absence of resonances, the absence of quartic resonances. Of course, it's not possible. So that's what I wrote here. So this system, the sum of Ci to the 1/2 with suitable signs is equal to 0, and the sum of Ci is equal to 0 as well. Now, it turns out that when we have four functions like that, it's not this equation will definitely have solutions. And there are two families of solutions. There are the so-called trivial resonances, which correspond to two of the signs being plus and two of the signs being minuses, two of the signs being minus, and the frequency being in this position, xeta minus xi minus eta, which will add up to 0. So these are the so-called trivial resonances. But these don't contribute to the growth of the energy because of the Hamiltonian structure of the system. But there's one more type of resonances which is special for the gravity waterways, which are the Benjamin-Ferrer resonances. And the Benjamin-Ferrer resonance, it turns out it's a special family of resonances. One can write them explicitly, but These are the so-called Benjamin Ferrer resonances. One of the frequencies is negative, 3 are positive, they all add up to 0, and the signs are in such a way that the big one, so the negative one, of course, is the bigger one. The big one just combine the small one, and the sums of the squares here is the same as sum of the other squares. And they are solutions of this system. So these are solutions of the resonance system. And it turns out that these are potential obstruction to the quartic energy inequality because they are going to do the quintic energy inequality because there's going to be a denominator. Only if we try to do the same argument, even assuming you understand the argument, how it works very well for the quartic one, even assuming you can manage the algebra to integrate by parts once more, those are going to end up as the denominators. And there's a certain important cancellation that was discovered by Dyachenko and Zakharov, namely that the multipliers that come up in the numerators after all the right symmetrizations, they become 0 on this set of resonances. So that's the ingredient there. And so our main contribution is to use that fact. That's an algebraic fact, but we have to use it in the context of designing an energy estimate that does not lose derivatives. So exactly how we divide, like what it means to divide is by this big expression. So that's part of our proof. Okay, so so we're going to talk about the expanded lifespan. So this is basically, this is part of our proof. So at the end of the day, what we proved, the first term that I discussed today was this quintic energy inequality for solutions of the gravity waterway system on large tori, and it turns out that so I'm going to move on to the next slides to the next theorem. I'm going to move on. I mean, I can just show it here. So basically, what we are saying is that we can using this theorem we can get the time of existence of size epsilon to the -6 essentially in the case of solutions of energy smaller than epsilon. So this is going to be our first application. Okay, so we are going to get back to this tomorrow. Thank you. Yeah.
When I see your theorem, for the initial condition, you have the first inequality. In your theorem to bootstrap, you need a second